Hi guys, Mr. Kane here. Today's topic is molecular polarity. So let's dig into it. So quick review. Polar bonds occur when one atom winds up having a higher electronegativity than the other. It's basically dependent on how well they share valence electrons. So for instance, if I had HF, and there was a bond between HF, this bond would be called a polar bond. That's because hydrogen has an electronegativity of 2.1, fluorine has an electronegativity of 4.0. We subtract those, we get 1.9, which shows up as a polar covalent bond. Okay? That means that these two electrons that are in this bond here wind up spending more time with fluorine than they do with hydrogen. They're still shared. It's just that fluorine's getting them 60, 70% of the time, whereas hydrogen's only getting them 30 or 40% of the time. We can represent the polarity of this bond two ways. We can draw our sigma negative, sigma meaning partially, to show that the fluorine's partially negative because it gets the electrons more often, and sigma positive over here to show that hydrogen is partially positive. Or we could choose to draw an arrow, a vector. Okay. Since we're chemists, we like to make our vectors fancy. It's just an arrow with a little plus sign on the end. That way we can quickly identify which end is positive and which end is negative without doing too much critical thinking. So when a molecule shows that it has an end that's partially positive and an end that's partially negative, it's said to be polar. Another way to say this is that it has a dipole moment. An interesting effect of polarity is that when you get polar molecules inside of an electric field, they wind up lining up in that electric field. One application of this is the MRI, the magnetic resonance imaging machine. If you've ever had an MRI of a body part, you know that they use really high magnetic fields to take pictures of what your soft tissues look like in your body, like say your muscles or your tendons in your knee or whatever. The way that they do this is that they use the really strong magnets to realign the water molecules that are in your body. And the water has different densities in different parts of the body, so they can see different layers and different tissues by just looking at the density of the water molecules that are lining up. So at this point, I think it's a good idea to take a look at some of the electronegativity aspects. Real basic idea here. We have two elements, A and B, and they both have very little electronegativity. Notice that the bond characteristic is showing that it's more like a covalent bond. And we're not seeing any difference in electronegativity. We're not seeing a dipole. If I crank up atom A's electronegativity to have a moderate amount of electronegativity, you can see that the bond character is starting to fluctuate in between covalent and ionic. You can also see that I'm getting partial charges to arise here because these two electrons that are in the bond between A and B are spending more time with A than they are with B. That's making A a little bit more negative, which here's our vector here. If I wanted to, I could change the electronegativity of B to increase its electronegativity. Notice that as I change the electronegativity of B to increase, it's decreasing the difference, which means that they're both getting the electrons just as often as each other. And that means that the dipole disappears. We have a non-polar bond. There's not a dipole here. We could push the electronegativity of B all the way up to the max here, and you'll see that now the difference in electronegativity makes B the more electronegative, so the vector is pointing towards B this time because it's the one that's more negative. We could take this to an extreme and keep going here, and we can show that if A and B have the same electronegativity, same large electronegativity, like they're both fluorine atoms, we wind up getting no difference in electronegativity. We get a non-polar bond. There are a variety of ways we could go about this. We could show an extremely polar bond. This one is so polar that we'd characterize it as ionic. A has almost no electronegativity and B has all of it. Very large negative charge on B, very large positive charge on A. As we said, molecules that are in an electric field will actually feel that electric field, so I could turn on an electric field here. And you see that nothing really happened because the positive plate over here attracts the negative B. I'm going to turn that electric field off, though. I'm going to shift atom A so that it's the negative atom, and atom B so it's the positive atom. What's going to happen when I turn on the electric field? Did you predict that? The molecule flipped. It's because Coulombic attraction. Opposites attract. Sometimes molecules have 3 atoms. Sometimes they have more. In this case, notice there's no polarity at all. I'm going to turn on the electric field. Absolutely nothing happens. Matter of fact, just for the sake of argument here, we could flip this over. We could turn the electric field back on. Nothing happens. That's because there's no charge to the molecule. There's no dipole. I can turn that off again. I'm going to return A to the left side. What if A winds up being a highly electronegative atom, whereas B and C are not? Well, if A is somewhat electronegative, that means that this end over here is partially negative. We see that B has a partially positive charge and Z has no overall charge on it at all. What happens if I turn on the electric field? Since there is a dipole in this molecule, we do see that the molecule reacts to being placed in an electric field. I'm going to shift that back around here. Now here's a curious question. What happens if C is just as electronegative as A? Notice C and A both I've set to the same setting. They both appear to be electronegative. I've got a partially negative and a partially negative over here. This is partially positive. Does this show a dipole? Will it react to an electric field? Doesn't look like it. Let's try this. Let's try if it goes this way. Will it react to an electric field? Doesn't look like it. Okay, so the thing is that we're only looking at the ends here, and the ends both wind up being partially negative. Since they're both partially negative, this does not show a dipole at all. And just for the sake of showing this off, we see something like this, where it's partially positive on the ends and partially negative on the inside. Now, will this show having a dipole? No, the electric field does nothing to it here. And I'm not going to reverse it because it's not going to do anything. Sometimes the molecule isn't in a linear geometry. It could be bent or tetrahedral or octahedral or trig-bippy. There's lots of different ways, but the ultimate question is, what happens if there's an angle that's not 180 degrees here? What happens if I have an electronegativity on atom A? Well, if I have an electronegativity on atom A, you'll notice that we do have a bond dipole here. And there is a partial negative charge, a partial positive, and no charge. If I put this in an electric field, what's going to happen? Notice it does orient itself in the electric field, and the thing that's orienting is the molecular dipole, not the bond dipole. In this case, they happen to be the same thing. I'm going to turn the electric field off. I'm going to rotate this back around, and I'm going to show what happens if atom C has an electronegativity also. Notice we have the two bond dipoles. We got partially negative, and we have a partially positive end over here. We have 3 different ends. Do we show that this molecule has a dipole? Turn on the electric field. We see yes, it does have a dipole. The overall dipole, you'll notice, isn't this bond dipole and it isn't this bond dipole. It's adding up these 2 vectors. It's the sum of them. More or less, it's the average. So we take a look in the middle of these 2, and we see that we have this yellow molecular dipole, and that's what's showing the attraction to the positive plate over here. We'll bring that back around. I'm going to reset this, And I'm going to ask what happens if I completely flip the situation. Oh, hey, notice as I bring the electronegativity down on atom A, check out where the dipole starts pointing. Because the bond polarity is that B is more negative and that C is more negative in this bond, that means that overall everything's pointing towards the right. One is pointing right and up, one is pointing right and down. That means overall to the right. The up and down basically cancel each other out. If I turn the electric field on in this situation, will it change its position? Not much, right? The overall dipole, the molecular dipole, is the one that's pointing towards the positive plate. What happens if I change atom C's electronegativity? Now it appears that both A and C are partially positive. B has a partially negative charge, which means that overall we've got a bond dipole here that's pointing up and to the right, a bond dipole over here that's pointing up and to the left. Right and left kind of cancel each other out, making there be just an upward dipole. So the overall dipole for the molecule is up. And if I turn on the electric field, you can see that the overall dipole is the one that's pointing towards the positive plate. This is actually a heck of a lot like what happens with water. The hydrogen, it would be represented by atoms A and C, and the oxygen is represented by atom B. Oxygen is more electronegative, so it gets the electrons in the bonds more often than the hydrogens. There are a lot of things to play with in this simulation. I'm going to leave a link to the FET on Google Classroom so that you can play with that if you like. Because you can change the angle greatly as well as the electronegativities. So you can see on our slide here that we have carbon dioxide. It's already been diagrammed for us that the oxygen is partially negative and the carbon's partially positive, or that these two vectors point outwards. Because the two vectors point outwards, left and right cancel perfectly. And this means that this is not going to have any polarity. If I put it in an electric field, nothing happens. In other words, no overall dipole. Here's the example of water that I was just talking about. You can see in our diagram over here on the side of A that the oxygen is partially negative, the hydrogen is partially positive. The vector that's drawn here for this bond shows down and to the right, while the vector here shows up and to the right. The up and the down components cancel, while the right and the right add up. So we get ultimately a vector that's shown to the right here. And we can see that inside of an electric field, the negative plate of the electric field lines up with the positive end of the water molecules. Now, what's really neat here is to think about this. These water molecules all have poles. They all want to line up as well in such a way that the negative pole of one water molecule lines up with the positive pole of another water molecule. Okay. A couple of quick summary slides here. What makes a polar molecule polar? Polar molecules occur when polar bonds are present. That has to happen. The polarity vectors will not cancel each other out. You got to think about the geometries because the angles that are there will or will not cancel each other out. So in other words, just because you get bonds that are polar doesn't mean that the overall molecule is polar. So typically what makes things nonpolar? Well, first off, any diatomic is going to be nonpolar. That's because you're taking hydrogen and bonding them together. Electronegativity 2.1 minus 2.1 is 0. That's a nonpolar bond. That's a no-brainer. If the orientation and the geometry are the same, and the terminal atoms are all the same, then you wind up getting something that's nonpolar. If the orientation is not the geometry, though, that means that there's lone pairs. That means there's different ends. We talk about symmetry a little bit. So if we don't see symmetry, then we wind up seeing polar molecules. Other ways to tell polar molecules. If you've got a binary compound with different atoms, it's probably going to be polar. Check the bond polarity first, but it probably is polar. If you've got a geometric shape where it is the same as the orientation, so trig planar, but you wind up with different terminal ends, you would wind up with a polar molecule because you have different terminal ends. You have different polarity vectors. Also, anytime you've got lone pairs around a central atom, it's probably going to be a polar molecule. There are some exceptions to this rule, but most of the time, lone pairs mean that the vectors will not cancel. So I think a good one to talk about might be CBr4. So we talk about CBr which is going to have, let's see, bromine has a total of 7 times 4 plus 4. So we get 32 valence electrons here. We're going to have a lone pair on each of the bromines, on each side of each bromine. It's not drawn on the very edge of the screen. There we go. So we've got something that's going to have a tetrahedral orientation as well as a tetrahedral geometry. That means that three-dimensionally it's going to look like this. And to keep from having too much garbage on my screen, I'm not going to draw any of the lone pairs on the bromine because they don't contribute to the overall shape of tetrahedral. All right, first thing I should do is I should check carbon to bromine. I should check the bond polarity here. Carbon minus bromine is 2.0 minus 2.8. And we get 0.8. That means that this is polar covalent. That means that the vectors that I draw wind up getting drawn out towards the bromine on all of them. Now, in order to understand how these vectors add up or don't add up, we need to be thinking in 3 dimensions. We need to remember that there's exactly 109 degrees between each of these bonds. They're all the exact same vector away. They're all the exact same angle away. And they're all pulling exactly the same amount. That means that they're going to cancel each other out. So this overall is going to be a non-polar molecule because these 4 vectors will wind up canceling each other out. Now, if we had instead CHBr3, the way that would look different is that the carbon to hydrogen would be a little bit different than the 3 bromines that I'm going to have to draw here. I'm going to draw these in. There's my wedge coming out of the screen. There's my dash going into the screen. Okay. Now, my carbon to bromine, I already know, is a polar bond. It's going to have the electrons spend more time with bromine than with carbon. But carbon to hydrogen is 2.1 minus 2.4. That's hydrogen, that's carbon. That's a non-polar bond. That means that I don't draw a vector here. What that means overall here for this drawing is that my 3 bromines all pull down. One pulls down and forward, one pulls down and back, one pulls down into the left. But the hydrogen doesn't pull up at all. That means that there is an overall polarity to this molecule. There is going to be a dipole moments. The overall dipole moment for this molecule is going to be a vector that's going down.